Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
If you look up at the Milky Way tonight, you might think you're looking at a peaceful, eternal home.
Oh, absolutely.
Right, like just a quiet neighborhood of stars that has, always been there, totally untouched and unchanging.
Yeah, that is the common assumption.
But you aren't. You're looking at, honestly, a cosmic crime scene. It is built entirely from the shredded corpses of other galaxies.
That is a beautifully grim way to put it, but yeah, it's totally accurate.
Today, our mission is to act as galactic forensic investigators. We are tracking down the ghost of a lost, ancient dwarf galaxy that astronomers are calling Loki.
And the most unsettling part is that it isn't millions of light years away.
No, it's not.
It is hiding right here, like completely embedded within the structure of our own Milky Way right above our heads.
It's wild. It completely reframes how you look at the night sky.
It really does. And I want to establish the stakes here right at the outset, because tracking down Loki isn't just about, cataloging a few anomalous stars.
Right. It's bigger than that.
Way bigger. It is about fundamentally rewriting our understanding of how galaxies actually grow.
So we are literally reading the forensic evidence left behind by the universe's earliest building blocks.
Exactly. We're looking at this groundbreaking work by Federico Sestito and his colleagues.
Yeah.
And this is really about peering back to the most violent epochs of the cosmos to understand the literal architecture of our own existence.
Well, let's start with that architecture. Yeah. Because to even comprehend where this lost galaxy Loki came from, we have to kind of shatter the illusion of the Milky Way.
The majestic spiral illusion, yeah.
Right. The idea that it just, popped into existence is this solitary, majestic thing. The harsh reality is that our galaxy is a cannibal.
A cannibal,
It had to eat to grow.
Cannibal is definitely the most accurate, if slightly gruesome way to describe it. In astrophysics, we call it hierarchical galaxy formation.
Right.
Because the Milky Way did not form in isolation as this gargantuan structure we see today. It grew over billions of years.
By eating smaller guys.
Exactly. By consuming smaller galaxies. Astronomers politely refer to this as merging, but
I feel like that term is doing a lot of heavy lifting.
Oh, it wildly misrepresents the physics involved.
Right, because merging makes it sound like, two companies shaking hands and agreeing to share an office building.
The very peaceful corporate merger.
Yeah, a neat mutual agreement. But I imagine the mechanics of these early galactic epochs were anything but neat.
Far from it. When we look back at the early universe, we see these smaller systems, these dwarf galaxies.
The little guys.
The little guys, yeah. And they served as the foundational building blocks of the cosmos.
Okay.
So as the proto-Milky Way began to grow, its immense gravitational well would essentially catch these smaller galaxies.
Like a spider web.
Sort of, but much more violent. Because when a dwarf galaxy falls in, it doesn't just slide neatly into a designated orbit.
What happens to it?
It encounters something called tidal forces.
Wait, like the tides on Earth, like the moon pulling the oceans.
Exactly like that, but on a massive, terrifying galactic scale. The gravity on the side of the dwarf galaxy closest to the Milky Way is pulled significantly harder than the side facing away.
Oh, wow. So it's literally being stretched.
Stretched until it hits a critical breaking point, yes.
That sounds intense.
It is. The immense tidal forces of our growing galaxy would literally tear the incoming dwarf galaxy apart. It is a complete dissolution of the original structure.
So they don't survive the fall?
Not at all. They disperse everything they have. Their stellar populations, their vast reservoirs of interstellar gas, their halos of dark matter.
Just gone.
Violently stripped away and scattered directly into the chaotic, swirling mass of our forming proto-galaxy.
I'm trying to picture the sheer scale of that.
It's hard to wrap your head around.
It's like, okay, imagine having a sprawling metropolis, let's say Tokyo or London.
Okay, good analogy.
And this city slowly expands outward over the centuries. As it grows, it swallows up all these independent neighboring farming towns.
Right.
But it doesn't just annex them, It bulldozes their town halls, rips up their roads, and completely disperses their populations into the city grid.
Until you can't even tell where the original city ended and the farming towns began?
Exactly. The city just absorbs the raw materials and the people and completely erases the original borders.
The structural integrity of those independent towns is just gone forever.
Okay, let's unpack this, because here is where I really struggle with the whole galactic archaeology concept.
Okay, lay it on me.
If the Milky Way completely shredded these smaller galaxies, if it paved over those farming towns and violently mixed everything into a metropolitan soup,
Right.
how is it even physically possible to recognize what used to be a separate galaxy?
That is the million-dollar question.
Like, if I'm looking at 100 billion stars in the Milky Way, how can astronomers point to a specific star and definitively say, that one right there used to belong to a completely different ancient galaxy?
It's a brilliant question, honestly, because looking at the Milky Way today, it really does just look like a homogeneous soup.
Just a big glowing disk.
Exactly. But it turns out the universe leaves indelible fingerprints.
Fingerprints.
Yes. The initial violent shredding destroys the galaxy's overall structure, but it doesn't actually destroy the individual stars themselves.
Oh, I see. The buildings are gone, but the people are still walking around.
Precisely. And astronomers hunt for these absorbed alien stars using two incredibly powerful, highly specific clues.
Which are?
The eccentricities of their galactic orbits and their chemical composition.
Orbit and chemistry.
Orbit and chemistry.
Okay, let's tackle the orbit first, because I think the common assumption, at least for me, is that all the stars in the Milky Way are essentially just swirling around the galactic center in one big, flat, orderly carousel.
And for the vast majority of stars born natively within our galaxy's disk, that is generally true.
They behave themselves.
Right. They form out of the same rotating disk of gas, and because of the conservation of angular momentum, they move together.
They travel in relatively predictable circular paths around the galactic center.
Exactly. They are the native population.
So going back to the city thing, they are like cars driving smoothly along a multi-lane highway.
Yes. Perfect.
Everyone is going the same direction, staying in their lanes, moving with the general flow of traffic.
Exactly. But when you meticulously map the billions of stars moving through our galaxy, which, by the way, requires measuring not just their two-dimensional position in the sky, but their 3D velocity and trajectory.
Which is an insane amount of data.
It is. But when you do that, you occasionally find glaring anomalies.
Like what?
You find stars with highly eccentric orbits.
Now, eccentric in this context doesn't mean the star has a quirky personality.
No. We are talking about the physical geometry of its path.
Right.
Instead of a nice, flat, circular orbit that stays neatly within the galactic plane, these stars are on wildly irregular, highly elliptical paths.
What does that look like in 3D space?
Well, they might plunge straight down vertically through the galactic disk.
Just straight through the carousel.
Exactly. Or they might sweep incredibly far out into the distant, sparse galactic halo before diving aggressively back toward the intensely crowded center.
So going back to the highway analogy, an eccentric orbit isn't just a car changing lanes.
No, not at all.
It is a car completely ignoring the existence of the road. It's swerving perpendicularly across the median, cutting straight through the flow of traffic.
Completely disconnected from the direction everyone else is traveling.
That is terrifying.
Right. And if you see a vehicle doing that on a highway, your immediate logical conclusion is that the car didn't merge onto this road normally.
It definitely didn't accelerate down the on-ramp.
Exactly. Something must have violently thrown it across the lanes.
A crash.
A cosmic crash. In galactic kinematics, a highly eccentric orbit is the lingering kinetic scar of an ancient outside collision.
Wow.
What's fascinating here is that it is a dead giveaway that the star did not originate from the peaceful native disk.
The scale of that investigation is staggering to me. You are literally looking at a catalog of billions of moving points of light.
Billions, yeah.
Trying to isolate the few dozen that are driving across the median.
It takes meticulous patience.
You have to track their current X, Y, and Z coordinates in a three-dimensional map of space, measure their radial velocity, and then what? Rewind their mathematical paths millions of years into the past.
Just to see where they came from. Yes, the kinematic mapping is a monumental achievement in modern astronomy.
But wait, didn't you say orbit was only one clue?
I did. Orbit alone isn't enough to secure a conviction.
Why not? If a star is plunging vertically through the disk, isn't that proof enough that it's an alien interloper?
Well, not necessarily.
Yeah.
No, because a native star could, theoretically, be violently kicked into a bizarre orbit by a localized internal event.
Oh, like a domestic dispute instead of a foreign invasion.
That's a great way to put it. Like, a nearby supernova explosion could blast a native star off course.
Right.
Or a gravitational interaction with a passing giant molecular cloud.
Or a black hole.
Or a close encounter with a black hole, exactly.
Mm.
Any of those could disrupt a native star's circular path.
Okay, so a weird orbit makes it a suspect, but not definitely guilty.
Exactly. So to definitively prove a star is an alien artifact from a consumed dwarf galaxy like Loki, that wild orbit has to be paired with our second clue.
The chemical forensics.
The chemical forensics.
Right, the chemistry. And to understand why chemical forensics can identify a star as an ancient outsider, I feel like we need to take a detour.
Let's do it.
We need to look at the universe's heavy metal forges, because it's not just about what elements are in the star.
Right, it's about what elements aren't there.
Which brings us to stellar nucleosynthesis.
It does. It is the fundamental process by which the universe creates the periodic table.
Okay, let's bypass the absolute basics here, because we know the early universe was just hydrogen and helium.
Just a very boring, simple soup.
Right, and we know stars act as fusion reactors. But the concept of chemical generations is what matters here, right?
Yes, the generational aspect is crucial.
So the universe essentially has a family tree.
Exactly. Think about the very first generation of stars that ignited in the cosmos.
The granddaddies.
The granddaddies of the universe. They were forged purely out of pristine primordial hydrogen and helium. There was nothing else available. And these stars were massive. They burned fast, and when they died in violent supernova explosions.
And when they exploded,
they blasted newly forged heavier elements, things they cooked up in their cores like carbon, oxygen, and iron, out into the surrounding gas clouds.
So they basically seeded the surrounding space with a brand new recipe of elements.
They did. They polluted the pristine gas.
So the next generation of stars that formed out of those enriched gas clouds inherited a tiny fraction of those heavier elements.
Exactly. They started life with a slightly more complex chemical makeup.
They lived their lives, fused even heavier elements, exploded, and handed an even richer chemical cocktail down to the third generation.
It is an ongoing multi-billion-year cosmic recycling program. Every generation gets more chemically complex.
Our sun is a beneficiary of this recycling.
Right, a huge beneficiary. It's a relatively late generation star.
Which is why if you look at its chemical spectrum, it is loaded with heavier elements.
Exactly. But astronomers use a specific, somewhat idiosyncratic terminology to describe this.
Oh no, what do they call it?
Well, in astrophysics, anything heavier than helium on the periodic table is simply referred to as a metal.
Which is completely wild.
I know.
Like to a chemist, calling oxygen or neon a metal is grounds for having your degree revoked.
Oh, it drives chemists absolutely crazy, but for us, it gives us a vital shorthand.
Okay, so if everything heavier than helium is a metal, how does that help us find old stars?
Because astronomers refer to stars with relatively small amounts of these heavier elements, specifically elements like iron, as metal poor.
Metal poor. So what does this all mean for our investigation?
Well, this is the crux of the chemical fingerprint. Because if you find a star that is extremely metal poor...
It means it didn't get the good stuff.
Exactly. It means it did not have the benefit of many previous generations of cosmic recycling.
So it must be incredibly old.
It must have formed very, very early in the universe's history out of gas that was still mostly pristine.
That is so cool. An extremely metal poor star is essentially a rough draft of a star.
A rough draft, yes. It is a literal fossil from the dawn of time, sitting right there in our galaxy, virtually untouched by the billions of years of chemical evolution that happened everywhere else.
Wow.
And those early metal-poor dwarf galaxies were the exact raw materials that merged together to form the massive galaxies we see today.
Okay, so we have the two pieces of our forensic toolkit.
We do.
We are hunting for ancient, fossilized, metal-poor stars.
Yeah.
And we need them to be flying around on bizarre, highly eccentric orbits.
Check.
The next hurdle, though, is the sheer geography of the Milky Way.
A spatial problem, yes.
Where do you even begin sweeping for them? The galaxy is 100,000 light years across.
Right, and geography and timing are intrinsically linked in galaxy formation. Well, if we consider the timeline of how the Milky Way was assembled, those earliest building blocks, those ancient metal-poor dwarf galaxies like Loki, they merged into the forming proto-galaxy at the very beginning of the process.
They were the first bricks in the foundation.
Right, and because they were drawn into the gravitational well so early, the remnants of those systems, their dispersed stars,
should logically sink toward the bottom.
Exactly. They should populate the deepest inner regions of the Milky Way. They should be trapped in the dense core, or what we call the galactic bulge, and deeply embedded within the intergalactic plane.
That makes perfect physical sense. The material that falls in first ends up clustered in the middle under the weight of everything that piles on top of it later.
It's just gravity doing its job.
Conversely, the dwarf galaxies that were consumed much later on, long after the main structure of the Milky Way was already spinning, they would likely be scattered out in the expansive spherical outer halo.
Because they couldn't penetrate as deeply.
So the geographical rule of thumb should be early building blocks in the dense inner plane, late arrivals scattered in the sparse outer halo.
That was the standard model, yes.
But I hear a but coming.
Oh, a massive but. When astronomers actually conducted massive surveys of the galaxy looking for these extremely metal-poor stars, they ran headfirst into a massive, frustrating anomaly.
The map didn't match the territory at all.
Not even slightly.
What did they find?
Well, they found very metal-poor stars, sure. But frustratingly, almost all of them were being found far out in the outer halo.
Wait, what?
Yeah. Astronomers were desperately searching the intergalactic plane, where the oldest building blocks fundamentally should be, and they just weren't finding them.
Not in the numbers that their hierarchical models predicted.
Exactly. It was a severe mismatch.
It's like, okay, imagine excavating the foundation of an ancient ruin.
Okay.
You dig down expecting to find Roman bricks, but you find absolutely nothing but modern concrete. And then you realize all the oldest original Roman bricks are inexplicably scattered out in the surrounding grassy fields miles away.
It completely upends the logic of how the structure was built.
It makes no sense.
It was a literal crisis for galactic archaeologists. And it forced the scientific community to start making some very complex, somewhat strained assumptions to explain the discrepancy.
Because scientists hate a vacuum.
We really do. We need an explanation.
So what was the strained assumption?
Well, astronomers noticed that the few metal-poor stars they did manage to find deep in the galactic plane often had retrograde orbits.
Retrograde meaning they are orbiting the center of the galaxy backward.
Yes.
They're moving in complete opposition to the general rotational flow of the Milky Way's disk.
Exactly. So, because they needed an explanation for why these ancient stars were so rare in the plane, the prevailing theory became that retrograde stars in the plane were the true, rare remnants of early violent assembly.
Because you'd have to hit the galaxy pretty hard to end up going backwards.
That was the logic. The idea was that an early merger would be chaotic and violent enough to throw the consumed stars into reverse.
Okay, and what about the ones going forward?
Oh. Meanwhile, prograde stars, the ones moving forward harmoniously with the disk's rotation, were assumed to have been added much later by gentler accretion events that just naturally aligned with the spinning disk.
Wow, so they were basically forcing the puzzle pieces together because they didn't have enough data.
They absolutely were. They looked at the few retrograde stars they found and essentially declared a universal rule.
Prograde means one type of origin. Retrograde means a completely different type of origin.
Exactly. They assumed you couldn't possibly have forward-moving and backward-moving ancient stars originating from the same early event.
They thought it was physically impossible.
The assumption was incredibly rigid. Prograde and retrograde meant totally different epochs and completely different progenitor galaxies.
And that rigid assumption, that forced geographic disconnect, is exactly what makes this new study by Federico Cicito and his team so monumental.
It really is.
Because they didn't just find a missing puzzle piece. They found a puzzle piece that completely breaks the previous picture of how our galaxy was built.
It is a remarkable paradigm-shifting finding. Cicito's team focused specifically on sweeping the Milky Way's galactic plane using highly advanced spectroscopic surveys.
Looking deep in the concrete foundation.
Exactly. And against the odds of all previous searches, they successfully isolated a sample of 20 strictly metal-poor stars located right there, deep in the plane.
20 ancient, heavy metal deficient fossil stars.
Yes.
Existing exactly where the original gravitational theory said they should be, but where actual observational surveys had previously failed to find them.
Finding them at all was a massive triumph.
But their mere presence wasn't the real shock, was it?
No, it wasn't. The shocking detail, the data point that completely upended the models is how these 20 stars actually behave kinematically.
How they move.
How they move. Here's where it gets really interesting.
Okay, lay it on me.
When Cicito's team looked at the orbital dynamics of these 20 stars, they realized these fossils utterly defy what past theories demanded.
In what way?
Well, they all share those high eccentricities we discussed.
Right. They're all swooping and plunging on wild, non-circular paths,
Yeah.
cutting across the median.
Yes. But within this tight, exclusive group of 20 planar stars, the team found both prograde stars orbiting with the galaxy's rotation and the retrograde stars orbiting backward.
Wait, really?
Yes, both within the exact same sample.
That is insane. It completely shatters that deeply held assumption that retrograde and prograde planar stars must have come from different epochs.
Totally shatters it. Here they are, side by side, highly eccentric, ancient, and moving in complete diametric opposition to one another.
Imagine you're standing in the center of a massive circular racetrack where millions of cars are all driving clockwise.
Okay.
And you manage to spot a fleet of 20 incredibly old vintage cars.
The metal poor stars.
Right. And they're swerving wildly across the lanes. But the crazy part is, some of these vintage cars are driving clockwise, and some of them are driving counterclockwise, accelerating straight into oncoming traffic.
It would be terrifying to watch.
But then, when you look closely at their intricate paint jobs, you realize they all belong to the exact same racing team.
It is a perfect visualization of the kinematic chaos, and you have to stop and imagine the sheer, unfathomable magnitude of the gravitational violence required to create that reality.
It bends the mind.
You have a single, cohesive dwarf galaxy, our racing team, Loki. It falls into the terrifying gravitational well of the early Milky Way.
And it hits the tidal forces.
Right. The collision is so catastrophic that it doesn't just shred Loki, it rips the dwarf galaxy apart so violently that half of its stars are violently flung forward into prograde orbits.
And the other half.
Or whipped brutally backward into retrograde orbits, scattering them across the entire galactic plane.
Okay, wait, slow down. I have to push back here.
Go for it.
How does finding stars moving in completely opposite directions prove they are from the same galaxy?
What do you mean?
Well, if I see a car driving north and a car driving south, my first instinct is not, oh, they obviously came from the same driveway.
Fair point.
It makes no intuitive physical sense. How did the gravity of the Milky Way actually accomplish that? How does one single object split into opposite orbital directions?
It is deeply counterintuitive, I agree, until you look at the mechanics of tidal stripping during a galactic impact.
Walk me through it.
When a dwarf galaxy like Loki approaches the Milky Way, it isn't a point mass, right? It isn't a single solid rock.
No, it's a huge collection of stuff.
It is a sprawling collection of stars with its own internal rotation and a massive halo of dark matter. As it plunges into the Milky Way's gravitational field, the side of Loki closest to the Milky Way is accelerated faster than the side further away.
That's the stretching effect we talked about earlier.
Yes, but it is also interacting with the angular momentum of the Milky Way's massive spinning disk.
So the disk is dragging on it.
Essentially, yes. If Loki impacts the disk at a specific angle, what astrophysicists call the inclination angle, the immense tidal shock can literally unbind Loki's internal structure in a highly asymmetrical way.
Okay, so what happens to the stars on the front?
The stars on the leading edge of Loki get accelerated forward by the disk's spin, adopting prograde orbits that align with the Milky Way's rotation.
And the stars in the back?
The stars on the trailing edge lose angular momentum due to dynamical friction. They get violently yanked backward, falling into retrograde orbits.
Wow.
A single structural entity is essentially smeared completely across the kinematic spectrum.
It is chaos. Total absolute chaos in the early Milky Way.
It really was. But your skepticism is exactly the right scientific response.
Well, thank you.
Because if you are going to make the extraordinary claim that these diametrically opposed stars actually belong to the same original dwarf galaxy, you cannot rely on orbital models alone.
You need the paint job from the race cars.
Yeah, exactly. To prove these cars belong to the same racing team, Sestito's team had to look past the orbital paradox and conduct a rigorous elemental chemical autopsy.
Right, because the retrograde-prograde split makes them look totally unrelated on the surface.
Absolutely. So the researchers had to compare the deep chemical signatures of these 20 stars, not just to each other, but to stars out in the halo, to other known consumed dwarf galaxies, and to highly complex simulated stellar populations.
That sounds like an incredible amount of processing power.
Oh, massive amounts of data. And this chemical autopsy revealed a fascinating, deeply violent story about how the environment that birthed these specific stars was enriched.
What does they find?
When they analyzed the elemental abundances, the specific ratios of elements like carbon, magnesium, and calcium compared to iron, they found a very distinct, incredibly aggressive chemical fingerprint.
What exactly does that fingerprint look like? What makes a chemical signature aggressive?
The chemical enrichment of these 20 stars points exclusively to extreme, highly energetic events.
Like a...
We are talking about the ashes of high-energy core collapse supernovae, which are the explosive deaths of extremely massive stars.
The ones that live fast and die young.
Yes. We are also talking about hypernovae, which are even more energetic explosions, often associated with the core of a massive star collapsing directly into a black hole while the outer layers detonate.
A hypernova, that just sounds terrifying.
It is, and they also found signatures from fast-rotating massive stars that shed heavily enriched material into space at incredible velocities, and even the catastrophic element-forging collisions of neutron stars.
So the environment that birthed Loki wasn't some quiet stellar nursery.
No, it was essentially a cosmic war zone.
Just continuous, devastating, high-energy detonations rapidly seeding the gas clouds with these specific heavy elements.
Yes. But in a forensic autopsy, sometimes what is missing is just as critical as what is present.
What was missing?
In the complex chemical signature of these 20 stars, there is a crucial, glaring absence. There is absolutely no chemical evidence of white dwarf explosions.
Huh. Okay, stop. Why is that specific absence so important?
It's a huge clue.
What makes a white dwarf explosion chemically different from a massive star-going supernova? And why does its absence matter to Loki's story?
It all comes down to the cosmic timeline and the specific elements these explosions produce. The high-energy events we just talked about, massive core collapse, supernovae, and hypernovae, those happen very, very quickly on a cosmic scale.
Because the massive stars burn their fuel so fast.
Exactly. Massive stars burn through their nuclear fuel at an astronomical rate. They live incredibly fast, and they die young, usually detonating within just a few million years of forming.
They were the rock stars of the universe. Live fast, die young, leave a brilliant explosion.
Exactly. And when they explode, they primarily produce what we call alpha elements: oxygen, magnesium, silicon, calcium.
Okay, so that's the fast stuff. What about the white dwarfs?
A white dwarf explosion, known as a type Ia supernova, is a completely different beast, both chemically and temporally.
Because they come from smaller stars?
Right. A white dwarf is the incredibly dense, glowing remnant of a smaller, less massive star, much like our own sun.
So for a star to even become a white dwarf, it has to slowly burn through its fuel over billions of years, right?
Yes. It gently puffs off its outer layers and leaves behind that dense core. It takes billions of years just to form the white dwarf in the first place.
And then it explodes.
Well, eventually. For that white dwarf to actually explode, it usually has to be locked in a binary system, slowly, agonizingly siphoning gas off a companion star.
Like a vampire star.
Exactly like a vampire. It pulls material onto its surface until it reaches a precise mathematical threshold called the Chandrasekhar limit.
And then boom.
Once it hits that mass, the entire white dwarf detonates in a massive thermonuclear explosion.
Which produces a different chemical signature.
Yes. Type Ia supernovae are the primary producers of iron in the universe. But the crucial point is the delay time distribution.
The delay time distribution, meaning the time it takes for all this to happen.
Yes. It takes hundreds of millions, often billions of years, for a stellar population to start producing type Ia white dwarf explosion.
Oh, wow. I see it now. The timeline is baked into the chemistry.
Precisely. The fact that Loki's stars show all the chemical ashes of fast, massive core collapse supernovae, but completely lack the distinct iron-rich chemical ashes of slow white dwarf explosions gives us a definitive, indisputable timeline.
It means Loki didn't survive long enough to see its smaller stars turn into white dwarfs and explode.
Exactly. Loki was incredibly short-lived. It formed its initial bursts of stars. Those massive stars detonated and enriched the local environment with alpha elements.
And
then, before the slower white dwarfs had time to evolve, reach critical mass, and contribute their unique iron signatures, the entire dwarf galaxy was swallowed and violently ripped apart by the Milky Way.
its star-forming days were over.
Its ability to hold onto its gas and cook new elements was abruptly and permanently terminated.
It lived fast, died violently, and was completely dismantled before it even had a chance to reach middle age.
It's sad when you think about it.
It is, but that is such a tragic, beautiful piece of forensic deduction. The absence of an element tells you the exact moment the galaxy died.
It really is elegant physics. But, Sestito's team had to push the autopsy even deeper.
Why? Wasn't that enough?
Because they didn't just look at the types of explosions, they looked at the precise uniformity of the resulting chemistry across all 20 of these scattered stars.
Okay, this brings us to what the study refers to as the closed system clue.
Yes.
Because even with the lack of white dwarf signatures and the presence of hypernovae,
Right.
a hardened skeptic might still say, so what?
Right. They might ask, could these 20 stars just be a massive cosmic coincidence?
Yeah. Could they have formed in totally different parts of the early universe that just happened to have similarly violent, short-lived conditions and then randomly ended up crossing paths in the Milky Way's plane?
It's the essential devil's advocate question. We have to rule out coincidence.
How do you do that?
To answer it, the researchers looked at the statistical dispersion, the mathematical spread of what we call the XFA ratio in these stars.
Okay, XFA sounds intimidating. I need you to translate that out of astrophysics notation for us.
Fair enough. I can do that. In astronomical notation, XFA is simply a way of expressing the abundance of a specific element. Let's call it X.
Like magnesium.
Right, which could be magnesium or calcium or titanium, and you compare it to the abundance of iron, which is F.
Okay, so it's a ratio.
The brackets denote a logarithmic scale compared to our sun, but essentially it is a highly specific recipe.
A recipe?
Yes, it tells us the exact microscopic proportions of heavy ingredients that went into making the star.
So they are looking at the specific recipe of heavy elements compared to iron in each of these 20 stars and looking for variations.
And what they found was truly startling. With the exception of just one single star out of the 20, the targets show a noticeably mathematically narrower dispersion in their XeV ratios compared to stars in the broader galactic halo or the bulge.
Even at similar overall metallicity levels.
Exactly. The recipe was unbelievably consistent.
Let me try to put this into human terms to make sure I grasp just how definitive this is.
Go for it.
Imagine you walk into a massive stadium filled with hundreds of thousands of people.
Okay, that represents the galactic halo.
Right. You are trying to find people who are secretly related. So you look at their blood types.
A good starting point for a search.
You find 20 people scattered throughout the massive crowd who all have an incredibly rare blood type, say AB negative.
Okay, that's our rare violent chemical signature without white dwarfs.
Exactly. But having the same rare blood type doesn't guarantee you're from the same family.
No, it doesn't.
You could just be randomly scattered strangers who happen to share a broad biological trait.
Right. The skeptic could still argue it's a coincidence.
But then you sequence their DNA. You look past the blood type at the microscopic underlying genetic markers.
Yes.
And you realize that these 20 people don't just share a rare blood type. They share the exact same microscopic, highly specific genetic mutations down to the most infinitesimal detail.
The dispersion is zero.
Right. The dispersion or variation in their genetics is incredibly narrow.
Mm-hmm.
They aren't strangers who look alike. They are definitively, undeniably siblings.
That is a brilliant analogy. The exceptionally narrow XV dispersion is the DNA test that proves they are siblings.
So they have to be from the same galaxy.
The researchers stated explicitly that the elemental dispersions in these targets are so remarkably small that they are virtually identical to what you would mathematically expect to see in a closed system.
Okay, define a closed system in this context. Do you mean a single, isolated bubble where the gas was perfectly mixed before the stars formed?
Yes, exactly that. In astrophysics, a closed system means the dwarf galaxy had a deep enough gravitational well to hold onto its gas.
Despite the supernovae going off.
Exactly. It held onto the gas, allowing the violent supernovae to explode and thoroughly mix their newly forged elements evenly throughout the galaxy's interstellar medium before the next generation of stars formed.
Think of stirring a massive vat of soup until the spices are perfectly distributed.
Yes. If these 20 stars had come from two different formation sites, two different dwarf galaxies that fell into the Milky Way independently, the gas in those two separate systems would have had slightly different mixing histories.
Because they'd have different amounts of supernovae going off at different times.
Exactly. The chemical dispersion, the variance in the recipe from star to star, would be noticeably wider.
But it isn't.
But it isn't. The data is definitive. These stars formed in a single, perfectly mixed, isolated vat. They formed in Loki.
The data is undeniable. We have the chemical proof of a closed system.
We do.
But wait, if we accept that, this brings us violently back to the massive, glaring paradox we introduced earlier.
Ah, the kinematic paradox.
Yes, we just proved chemically beyond a shadow of a doubt that this is a single closed system. But we also know that half these stars are orbiting forward and half are orbiting backward.
It is a staggering contradiction on the surface.
Now, you explain how tidal forces could do this, but did the astronomers actually verify it couldn't just be two identical galaxies?
They absolutely did.
How can we be mathematically certain a single closed system produced stars orbiting in totally opposite directions?
Well, the orbital paradox sits at the very heart of this discovery, and the astronomers absolutely question this themselves. It is the natural scientific response to such bizarre data.
Right.
They had to ask. Despite the incredibly tight chemical similarities, is there any mathematical loophole where this could actually be a pair of systems?
Could Loki actually be Loki and, say, Thor?
Yes. One prograde dwarf galaxy and one retrograde dwarf galaxy that just miraculously happen to have identical chemistry.
Because if it's two separate systems, the orbital problem is neatly solved. One hit the Milky Way from the left, one hit from the right. Prograde and retrograde explained without needing extreme tidal unbinding.
It would elegantly solve the kinematic problem, yes. But Sestito's team didn't just guess. They ran the mass models of the star and gas material.
What does that mean?
They used complex n-body simulations and mathematical frameworks like genes modeling to reconstruct the mass required to produce these stars.
Oh, like working backwards from the wreckage.
Exactly. And the physics simply do not support the two-system theory.
Why not? Break down the math for me. Why does the two-system theory fail?
If you assume these stars came from two separate systems, one prograde, one retrograde, the total baryonic mass, which is the total mass of all the normal visible matter like gas and stars needed to form them, would have to be exactly double what we calculate for a single system scenario.
Okay, so you'd need twice as much raw material falling into the Milky Way at the exact same time.
Yes. Furthermore, and this is the mathematical nail in the coffin for the two-system theory, those two completely separate dwarf galaxies would have to share a nearly identical mirror image chemical history and evolution.
Which is just too much of a coincidence.
Way too much. They would have to have the exact same rate of high-energy hypernovae, the exact same precise timeline, resulting in the exact same lack of white dwarfs, and perfectly match that incredibly narrow Xe dispersion we just talked about.
To go back to my stadium analogy, that would be like finding two completely unrelated families from opposite sides of the world, throwing them into the stadium, and discovering their microscopic DNA mutations are completely identical.
Yes. It's not just unlikely, it's statistically absurd.
It is statistically impossible.
The mass models and the chemical forensics trap us into only one viable physical reality. Loki was a single, unified dwarf galaxy.
It was a closed system.
And it was subjected to an ancient accretion event so spectacularly violent, so profoundly disruptive, that the Milky Way ripped the galaxy's internal structure entirely apart.
Scattering its constituent stars across the massive plane of our galaxy in completely opposing orbital directions.
It's breathtaking, isn't it?
It really is. It completely rewires how I picture the space above our heads.
Same here.
The Milky Way isn't just a slow, gentle accumulation of dust. It is a violent history of catastrophic collisions. And by looking at chemical recipes in backward orbits, we have just successfully pieced together the brief life and the violent death of one of those victims.
We have isolated the ghost of Loki.
Incredible.
But, the most exciting part of Sestito's paper isn't just what they found, it is what this implies for the future.
There's more.
Oh, much more. The search for the Milky Way's violent history is really just beginning. The study explicitly notes that while this sample of 20 planar stars is enough to prove the concept and break old models, it is still a relatively small sample size.
It's the tip of the iceberg. It proves the ghosts are there, hiding in the plane.
Exactly. The future of galactic archaeology is incredibly bright because we are standing on the precipice of a massive data explosion.
What's coming next?
The study points specifically to the next generation of larger, homogeneous spectroscopic surveys that are coming online soon. Facilities and instruments like WEAVE and Foremost.
Explain what WEAVE and Foremost are going to do differently.
These are highly advanced multi-object spectrographs attached to massive telescopes. Instead of looking at a few stars at a time, they use thousands of optical fibers positioned by robots to simultaneously capture the light from thousands of stars at once.
Oh, wow. So they can survey the sky much faster.
Exponentially faster. They are going to survey millions of stars across the galactic plane with a level of chemical and kinematic precision we've never had access to before.
That's huge.
If Loki is out there, represented by these 20 scattered stars, weave, and foremost are going to find hundreds, maybe thousands more of its siblings.
They will map the full extent of its shredded remains.
They are going to illuminate the entire cosmic graveyard. They will clarify the origins of planar metal-poor stars and undoubtedly uncover the ghosts of other dwarf galaxies we don't even have names for yet.
It will be a golden age for understanding the violent assembly of our home.
It is just spectacular science.
So the next time you are out on a clear night and you look up at that glowing, milky band of light stretching across the blackness, I want you to change how you see it.
Think of the violence.
Right. You aren't just looking at our galaxy.
Yeah.
You aren't looking at a peaceful, static home. You're looking at the ultimate cosmic graveyard.
You are looking at the ghostly remains of countless ancient dwarf galaxies shredded billions of years ago, with their constituent stars still swirling in chaotic, invisible orbits right above our heads.
And if we really want to push that thought to its absolute limit,
Let's do it.
consider the geometry of what we just discussed. If the stars of Loki and other consumed systems like it were scattered so violently that they are still currently plunging across the galactic plane in wildly opposing, highly eccentric directions,
Yeah.
is it possible that our own relatively young solar system, on its quiet circular path through the disk, will eventually cross paths with, or even be subtly gravitationally nudged by, the silent ancient ghosts of an entirely different lost galaxy?
Now that is something to think about.